In the second part, we will see some details regarding action potential. This is something very similar to the things we saw in the muscle chapter. First, let's remind ourselves about membrane potential. We said this is a status set by the membrane, since the membrane is separating ions, different ions and particles are charged particles from inside and outside. This will create two different areas. The distribution of the ions in these two areas is different, okay? And therefore, in general, we will have more positive netted charge outside and more negative netted charge inside. At the same time, we already talked about that there are several types of gated channels. There is a ligand gated channel. Usually this is a chemical gated channel. So there is a chemical structure, a chemical compound that will come and bind to the gate in order to open the gate. Okay, this is like the case of ACH, acetylcholine, and the sodium gates, sodium and maybe even potassium gates. Okay, then we have mechanical gated channels. So for example, if there is a mechanical force that is applied on the cell, this will cause these gates to open. Think, for example, if you remember the lamellar corpuscle. If you remember, we said this is for deep touch or deep pressure. And how does it feel the deep touch or deep pressure? Simply because it has mechanical gated channels. So the deep touch would stimulate these channels to open. This is another form. And then there is a third form, that is the voltage gated channels. The voltage gated channel is closed when the cell at rest, meaning that it's positive outside, negative inside. But however, if this charge is flipped, the gate will open. Or if this charge is changed at certain level, the gate will open. Okay, so these are the three different types of channels in the plasma membrane. Mainly we are going to deal with the voltage gated and with the ligand or chemical gated channels. Now, for the membrane potential, we have some changes that happens there, and these changes not necessarily would lead to action potential. What does this mean? It means that there are in the membrane, okay, in the membrane there are always attempts to open the gates. There is always sodium, for example, trying to rush inside, and there is always potassium trying to get outside. So there is always trying to change the distribution of these channels. Now, when sodium comes inside, we already saw in the muscles that this would lead to action potential, right? Very general, that's how we put it. In reality, this is not really what's happening. The cell, some cells or some neurons and even some muscles can accept a few sodiums to come in, okay? But this not necessarily would give or would lead to release of action potential. These will cause, yet they are going to cause changes. It will cause changes in membrane potential, but not to the degree to have action potential. These small changes, we will call them graded potentials. Okay, so the graded potentials are local changes in the membrane potential. Local changes in the membrane potential, or you can say small changes in the membrane potential. They are not strong enough to induce action potential. Only strong stimulations would induce action potentials, meaning that we have a huge amount of sodium ions rushing inside the membrane or inside the cell. These would usually lead to action potential. So Let's see this graph. Here at minus 70, this is the resting membrane potential, right? Now you can see that there are changes in these membrane potentials, okay? Some of them small, some of them big, and some of them are significant, like this one. This one, it will exceed the minus 55 line. This minus 55 in this case is something called the threshold. The threshold, we can describe it as the minimum change in membrane potential to have or to induce action potential. This is the minimum change in the membrane potential that is needed to have an action potential. So any changes in the membrane potential that does not, or any changes in the membrane potential that do not reach the minus 55, these are all graded potentials. All of them are graded potentials, that they are very small and very local. They are not going to cause an action potential. And technically this one, if we want to be accurate about drawing it, it should go all the way to plus 30, since it's crossed the threshold. Since it's crossed the threshold. So these are graded potentials. Now, for these graded potentials, they can cause depolarization, as you can see here. If we are moving away from the resting membrane potential, this is called depolarization. We are moving away toward more positive value of the membrane potential. If you remember in the muscles, we said we have depolarization and then repolarization, right? So since this is moving away from the minus 70 or the resting state, this is depolarization. They are still graded potentials. They are still small. They did not reach the threshold, but they are depolarization. So this is one form of graded potentials. The other form, that these changes are happening into the opposite way, meaning that they are going even to more negative value. These are called hyperpolarization or hyperpolarizing graded potential. It means you are increasing the polarity of the membrane. We are not losing it. Here we are losing the polarity. No, here we are increasing the polarity of the membrane. So this is the second type of the graded potential. Usually, with depolarizing graded potentials, the neurons will be more sensitive to changes. So here the neurons will be much easier to have action potential. They are stimulated or alerted. They are more susceptible to changes or to induce action potential. Whereas here they are not. They are less sensitive. Okay? They are less alerted. They are more relaxed for changes. So in this case, with the hyperpolarizing graded potential, we need even much stronger stimulus to reach to the threshold. To understand this better, let's do some drawing here. Think of this: if you have a stair, okay, and you are in normal situation, you are standing here, okay, and you want to go to here. Say for example, you are going to consume in this trip 100 ATPs, okay, assuming. So this is a normal situation. But if you are standing here to here, you will need maybe like just 50 ATBs. Okay, you are close to the target area. This is depolarizing. This is the situation of the depolarizing graded potential. Okay, you are closer to the threshold. But if you are standing far away, like here, you need to have to reach to this area, and then you have to reach to this area. So this is like, it needs 100 ATBs, and here you need another 100 ATBs. So here you are very likely, less likely. So here you are less likely to reach your target. Why? Because you need more stimulus. You need stronger stimulus. You need, in our example, you need more energy to reach into this area first and then to this area. So this is what will happen with the hyperpolarizing graded potential. Think, for example, if you go to the dentist and they will inject you with anesthesia, right? Anesthesia, that's what it's causing to the neurons. It puts them into hyperpolarizing situation, that the pain has to be much stronger in order to feel it. Okay, that is the hyperpolarizing graded potential. So I will stop here. When we come back, we will start talking about the action potential.